Have you ever stopped and wondered how an AI like ChatGPT can just write a poem, or summarize a huge article, or just chat with you like it gets what you're saying? I mean, it really feels like magic, right? Well, today, we are going to pull back that curtain and look at the revolutionary tech that makes it all possible. And it all starts with a pretty simple question.
Right. This is the fundamental challenge. For you and me, a sentence like "the cat is cute" has instant meaning. We get it. But for a computer, that's just a bunch of characters. It doesn't mean anything. So how do you bridge that massive gap? How do you actually teach a machine to understand not just the words, but the relationships between them, the context?
So, the very first attempt to solve this was honestly brilliantly simple. Before an AI could even think about context or nuance, it had to learn to see words the way it sees everything else in the world, as numbers.
This early method, called bag of words, is exactly what it sounds like. The model would literally just take all the words from a sentence, throw them into a virtual bag, and then just count them up. So a sentence like, "My cat is cute," becomes a simple numerical code, what we call a vector, of ones and zeros, just flagging which words are there. It was a really clever start for sure, but it had a huge blind spot.
Yeah, see, a bag of words model knows that the words cat and cute are in the sentence, but it has no clue how they relate to each other. My cute cat and that cat is cute would look really similar to the AI, but so would "is that cat cute," which has a totally different intent. The order, the nuance, the meaning. It's just completely lost.
Okay, so counting words wasn't enough. It was pretty obvious that AI researchers needed a much smarter solution. They had to figure out a way to not just count the words, but to actually capture their rich, complex meanings. And the answer they came up with was a technique called word embeddings. Now, the core idea here is to forget simple counting. Instead, what if you could map every single word to a long list of numbers, hundreds of them, in a vector? Each of those numbers represents some kind of hidden property or attribute of the word that the model learns all by itself.
And this is where it gets pretty amazing. So you look at a word like cats. It gets a high score for concepts the AI figures out are related to animal and plural. A word like baby scores high on things like newborn and human. And the craziest part? These attributes aren't programmed in by people. The AI figures all these relationships out on its own, just by analyzing billions and billions of sentences. All of a sudden, every word has this rich numerical identity.
So here's the magic. When you plot these vectors out in this kind of multi-dimensional space, words that have similar meanings naturally start to cluster together. Cats, dog, and puppy all become neighbors. Apple and banana are hanging out in the same area. This is how an AI learns meaning, not from a dictionary, but from proximity. It gets that a puppy is kind of like a dog because their numerical identities are just so close.
Okay, great. So we've figured out how to give words meaning. But how do you process them in an actual sentence? Well, for a long time, the approach was to do it just like we do, one word at a time.
These earlier models, like recurrent neural networks, or RNNs, would read a sentence. Let's say, "I love llamas," step by step. It reads "I," then it reads "love" while trying to remember "I," then it reads "llamas" while trying to remember both "I" and "love." Now, this works okay for short sentences, but imagine a long paragraph. It's like trying to remember the very first word after reading 1,000 others. The context just gets lost along the way.
And this limitation, this problem of forgetting, is really what set the stage for one of the biggest breakthroughs in the entire history of AI. The question became, what if, instead of reading word by word, a model could just see the entire sentence, all at once?
In 2017, researchers from Google published a paper with this now famous title. And it didn't just propose a new model. No, it proposed a completely new way of thinking about language, and it was all centered on this one powerful mechanism called attention.
So this new architecture, the transformer, it completely threw out that one word at a time idea. Its huge breakthrough is something called self-attention. And here's the basic idea. For every single word in a sentence, the model asks a kind of question, a query, about its own context. Then it compares that question to a key from every other word in the sentence to figure out how relevant they are to each other. This lets it precisely weigh how much attention each word should pay to every other word. And because it does this for all words at the same time, it can be trained in parallel, which makes it unbelievably fast and powerful.
Probably the best way to think about the original transformer is like a super smart translator that has two main parts. First, you've got the encoder, which is like the reader. It reads the entire input sentence all at once, building this incredibly rich contextual understanding of everything. Then, you have the decoder, the writer.
It takes that deep understanding from the reader and starts generating the new sentence one word at a time, but it's always aware of the full context of the original sentence.
And we're not just talking about one reader and one writer. The real power here comes from stacking these components, layer on top of layer on top of layer. Each new layer deepens the model's understanding, allowing it to grasp incredibly complex grammar, syntax, and all the little nuances of language. Stuff that was way beyond what the old sequential models could ever hope to do.
So this single architectural shift back in 2017 didn't just make translation better, it kicked off a whole new era for artificial intelligence. A complete game changer.
I mean, this timeline really says it all. Before 2017, progress was steady, it was fine. But after that Transformer paper dropped, it was an absolute explosion. All the big names you hear about today, BERT, T5, and of course, the entire GPT family that powers ChatGPT, they are all direct descendants of this one brilliant idea.
And what's so fascinating is how developers took that original reader-writer design and started to specialize it. So some models, like BERT, they just use the encoder, the reader part, which makes them fantastic at tasks that need deep understanding, like Google Search. Then you have others, like GPT, that just use the decoder, the writer, which makes them incredible at generating creative text. And all of this complex architecture boils down to that simple prompt and response that you use every single day.
All right, so after this whole journey, from counting words in a bag all the way to these massive, complex architectures, what is the single most important thing to take away from all this?
It all comes down to this one idea. That attention mechanism is the AI's superpower. It's the ability to look at an entire sentence at once, weighing every single word against every other word simultaneously. That's how it knows that in the sentence, the robot picked up the heavy metal block, the word heavy describes metal. But in the sentence, he loves heavy metal music, it knows heavy metal is a single concept. This deep, instantaneous grasp of context, that is the secret sauce behind the entire Transformer revolution. It's not magic, it's just paying attention to everything all at once.